Hi, this video we're going to talking about another type of the open system device, which is we call throttling device. Okay, so throttling device is basically a device that reduces the pressure. The way they reduce the pressure is because they have either adjustable valve here or some portable plug, and so they will restrain the flow. And so consider, for example, fluid flow through this one entrance and one outlet porous plug. The fluid will have a pressure drop, and this is example we see in our reality. You have at the back of your refrigerator, you will see this expansion valve. That's actually a throttling valve. We call capillary tube. It's something like this. Okay, so how is this component to work? What is energy conservation look like, right? So we start with our equation for mass conservation. So which means all the inlet mass flow rate coming in is going to be equal to mass flow rate going out. And since this is just one, right, one inlet and one outlet just coming in here and leaving here, so we can get rid of our summation. That means mass flow rate coming in is going to be equal to mass flow rate coming out. It's a constant. So that's our mass conservation equation. Now let's focus on energy conservation equation. Energy conservation equations start with this original equation. Since it's a steady state device, which means the energy rate coming in is equal to energy rate going out, and this energy has components. The first one is a heat transfer coming, and it could possibly have work transfer coming. And since it's open device, the mass flow rate coming is going to have enthalpy and kinetic energy and potential energy. Here I'm actually get rid of the sigma, right? Because it's one inlet. And then the right hand equation, it's the same, except we're going to change everything out into out. And again, we can get rid of the sigma because it's just one outlet, and h plus half v squared plus gz. Okay, now let's think about this equation. We're going to make some assumption. What is assumption we're making for throttling device, okay, or expansion valve? We consider there's no heat transfer. It's well insulated. We assume there's no work done. There's no required work. There's no work generated out. So there's no work transfer rate. We also consider there's no kinetic energy change. This stays constant, so change will be 0. We also consider there's no potential energy change. That's equals 0 as well. So go ahead, let's get rid of the heat transfer. There's no work in and out. Also, there's no kinetic energy change and no potential energy change. Well, it's astonishing to find out what's left, right? So we have this mass flow rate times H, which is inlet H1, and this is M1 inlet, and equal to the right hand will have mass flow rate leaving out and enthalpy at the exit. Well, from the mass conservation equation, we know m1 dot is equal to m2 dot, so then we can cancel that out as well. Then the equation we're getting is h1 equals h2. That is the energy conservation equation for throttling device. H1 equal to H2, which means it's gonna be isenthalpic. Iso means the same, right? Enthalpy, so isenthalpic process, which means the enthalpy stays the same. Okay. So now let's look at one special scenario. If I'm looking at this special case, which is this throttling valve, this is how we draw. And if the substance going through is ideal gas, doesn't have to be. Often, for example, for refrigerator, we are using R134 refrigerant or freon passing through, right? But here, if it's ideal gas, what happens going through this throttling valve? Because if it's throttling valve H1 equal to H2, we also learned H for ideal gas, it's basically a function of a temperature, right? If enthalpy stays the same, that we can conclude T1 is equal to T2. The temperature stays constant. Another way to prove this, we can look into this way. Delta H will be equal to 0 since H1 equal to H2. And delta H for ideal gas, remember one of the methods is going to be Cp at, let's use T average times T2 minus T1. If that equals 0, Cp of course is not equal to 0. So the only way to make it 0 is T2 minus T1 equal to 0. Then we prove again T1 equal to T2. So yeah, in other words, we can make a conclusion for this special case. If it's ideal gas, the temperature stays the same during this throttling process. Okay. So here's a question for you. Do you think if it's not ideal gas, if I put R134 in there going through this capillary tube, what do you think about the temperature? Will the temperature drop a lot, like what we want it to be? Because that's how it causes cooling for our refrigerator, right? But why so? So that's going to be a topic for the next video. We're going to use R134 as an example to show the temperature drop dramatically during this throttling process. Okay, so that's all for now, and we'll see each other next time at next video. Bye now.